Some modern farms now harvest more food in a single day than entire farming communities once produced in a year. Across massive agricultural regions, machines worth millions of dollars operate almost nonstop, racing to move crops from the field before quality drops, prices collapse, or weather destroys entire harvests overnight. Modern agriculture is no longer driven by manpower alone. It has evolved into a gigantic food production network powered by robotics, AI systems, hydraulic machinery, and industrial-scale logistics operating at astonishing speed. In Washington state, the apple capital of the United States, harvest season begins with machines that look more like heavy construction equipment than traditional farm tools. Giant hydraulic apple shakers roll through the orchards weighing nearly 10 tons each. Their mechanical arms clamp tightly around tree trunks before unleashing violent bursts of vibration strong enough to send thousands of apples crashing down within seconds. Entire orchards suddenly erupt into storms of falling fruit while dust and leaves explode across the rows beneath the trees. Then another fleet of machines immediately takes over. Windrowers sweep through the orchard, pushing mountains of apples into clean, organized rows, before pickup harvesters glide across the ground with rotating rubber fingers skimming just above the soil. The system lifts apples upward onto fast-moving belts, while giant air systems blast away leaves, dirt, and debris. Within minutes, tons of fruit are transferred into storage bins, ready for transport toward giant juice and food processing facilities operating around the clock. One harvesting system can replace dozens of workers during peak season, while gathering up to 15 tons of apples per day. But the violence of the process creates another problem: bruising. Apples damaged during impact lose much of their value in premium fresh markets, and are often redirected toward juice concentrate and industrial food manufacturing instead. In modern agriculture, appearance alone can change the economic value of an entire harvest. That pressure pushed manufacturers to engineer a far more advanced system. New generation apple harvesters now deploy giant padded catch frames beneath the trees before shaking even begins. Instead of slamming into the ground, the apples land softly inside controlled collection platforms before moving directly into storage containers. That single innovation dramatically increased the amount of export-grade fruit capable of surviving international supply chains without damage, and the stakes behind it are enormous. Apple orchards require years of investment before producing serious commercial harvests. A poor season doesn't just reduce profits. It can threaten the survival of entire farming operations already carrying massive equipment, irrigation, and labor costs. That financial pressure is rapidly accelerating the next major shift in agriculture: artificial intelligence. AI-powered harvesting robots are already entering commercial orchards equipped with machine vision. Cameras capable of identifying ripe apples with remarkable consistency, instead of shaking entire trees violently. Robotic arms carefully extend toward individual fruit before twisting and removing each apple with controlled movements designed to minimize damage. Some robotic systems can now operate day and night with almost no interruption, harvesting thousands of apples while reducing waste dramatically. And this transformation is spreading far beyond apples. In Europe, another massive operation unfolds underground during carrot harvest season. Machines like the Grimm Evo 280 move across enormous fields in countries such as Germany and the Netherlands, functioning almost like mobile processing plants. Underground lifting systems pull huge waves of carrots from the soil, while rotating cleaning mechanisms shake away dirt in seconds. Spinning cutters slice off the leafy tops, while onboard sorting systems separate the crop before workers even touch the product. From above, the visual effect is mesmerizing. Endless streams of bright orange carrots surge across synchronized belts, while multi-ton harvesters continue moving steadily across the fields. One machine can replace hundreds of laborers while operating nearly non-stop throughout peak harvest weeks. But not every crop can be harvested immediately. Onion farming follows a completely different strategy. Instead of collecting the onions directly from the soil, specialized windrowing machines carefully lift the bulbs and place them into long rows beneath the open sun. There they remain for days, while the outer skins slowly dry and harden naturally. This curing stage is essential for long-term storage and global transport, allowing onions to survive extended shipping without rapid spoilage. But curing onions in open fields creates another risk entirely. Sudden rainfall during this stage can trigger mold outbreaks capable of wiping out huge sections of the harvest. Entire farms monitor weather systems constantly during curing season because one unexpected storm can erase months of work almost overnight. Once drying is complete, pickup harvesters return to the fields using rotating tines, cleaning brushes, and air systems to gather the onions while removing loose dirt and damaged skins. Premium onions move toward fresh produce markets, while lower-grade crops are redirected into industrial food processing. And this is what modern agriculture has become. Not simply planting and harvesting crops, but operating enormous interconnected systems where machinery, weather, timing, food quality, and global demand are locked together in a nonstop battle for efficiency. Before modern farms can harvest millions of tons of crops, they first have to rebuild the ground itself. Across enormous agricultural regions in Europe and the United States, giant tractors drag multi-ton plows through hardened soil with enough force to rip open layers buried nearly 70 centimeters beneath the surface. This process goes far beyond simple tilling. It is a full-scale underground reset designed to restore airflow, improve water absorption, and break apart compacted earth that can choke root systems and reduce crop yields dramatically. As the machines advance, massive steel blades roll huge waves of soil upward, while clouds of dust explode behind them. Some tractors generate more than 600 horsepower, pulling oversized tillage systems across hundreds of hectares, from sunrise until long after dark. Fuel burns continuously, engines roar across the fields nonstop, because in large-scale agriculture, poor soil preparation can reduce yields long before seeds ever enter the ground. Once the deeper layers are loosened, another category of machinery takes over. Shallow tillage systems move across the upper soil layer using rotating blades and calibrated cutting discs to create ideal planting conditions. Dry vegetation, leftover crop residue, and organic material are blended directly into the surface, gradually transforming the soil into nutrient-rich humus, capable of supporting the next production cycle. At the same time, weeds are uprooted while pests hidden beneath the surface are exposed to heat, air, and sunlight. Within hours, rough, uneven terrain becomes a smooth planting zone engineered for high germination rates and large-scale mechanized farming. Then comes one of the most advanced planting systems in modern agriculture. Giant GPS-guided seed drills. Some stretch more than 20 meters wide when fully unfolded, covering enormous sections of farmland with astonishing efficiency. Mounted above them are oversized seed hoppers capable of carrying several tons of seed at once. As the machines move across the fields, thousands of seeds travel through complex tube systems before dropping into the soil at tightly controlled depths and spacing intervals. Every row is computer-guided. Every movement constantly adjusted through GPS correction systems and onboard sensors, monitoring seed density, planting speed, and soil conditions in real time. Some systems can even deactivate individual planting rows automatically to eliminate overlap and reduce seed waste across irregular field shapes. The economic impact is enormous. Saving only a small percentage of seed loss across thousands of hectares can translate into huge increases in seasonal profit. Modern planting has become less about scattering seeds and more about maximizing efficiency across entire agricultural networks. But no matter how advanced the machinery becomes, every major farming operation still depends on one resource above all: water. That challenge led to the rise of one of the most recognizable structures in industrial agriculture: center pivot irrigation systems. From the sky, they appear as giant green circles carved directly into dry landscapes across America. On the ground, the scale feels almost unreal. Long irrigation pipelines mounted on wheeled towers slowly rotate around central hubs like enormous mechanical clock hands, stretching hundreds of meters across the fields. As the systems move, rows of sprinklers distribute water evenly across the crops, while sensor-driven monitoring systems constantly adjust flow rates based on soil, moisture, temperature, and weather conditions. Some irrigation networks can now be controlled remotely through smartphones or automated management software capable of optimizing water delivery down to specific sections of a field, in places like Nebraska and Arizona. These systems help transform dry semi-arid land into some of the most productive farming regions in the world. Corn, soybeans, peanuts, and wheat now grow at massive scale in areas that once struggled to support large amounts of vegetation. But this level of automation also creates new vulnerabilities. During extreme summer heat, even short irrigation failures can place enormous stress on crops within hours. A damaged pump, broken pipeline, or electrical malfunction can threaten entire fields before repair crews even arrive. Some farmers now monitor irrigation systems through the night because mechanical breakdowns during critical growth periods can trigger devastating financial losses, and the machinery never truly stops moving. During planting season, tractors, seed drills, irrigation systems, supply trucks, and support vehicles operate continuously across giant agricultural corridors, like synchronized industrial convoys, moving across the landscape. If you've never seen agriculture operating at this scale before, subscribe now, because the next harvesting systems become even more extreme. Entire fields will soon be flipped upside down by machines designed to gather crops at speeds almost impossible to believe. Few harvesting operations in modern agriculture look more violent or more satisfying than peanut farming. Unlike crops growing above the surface, peanuts spend most of their life hidden underground, attached to tangled root systems beneath the soil. And when harvest season finally arrives, entire fields are turned upside down by machines built specifically to rip those hidden crops out of the earth at astonishing speed. The process begins with the digger shaker. Long underground blades slide beneath the peanut plants before suddenly lifting entire rows upward in one sweeping motion. Massive shaking systems immediately begin rattling the roots, blasting away dirt while exposing clusters of peanuts hanging beneath the vines. Then the machine flips the entire plant upside down and lays it neatly across the field to dry under the sun. Within minutes, the landscape changes completely. Bright green fields transform into endless patterned rows stretching toward the horizon while dust drifts through the air behind the harvesters. The visual effect is almost hypnotic. But peanut harvesting depends heavily on maturity timing. If the crop is pulled too early, the peanuts contain lower oil content and reduced flavor quality. Wait too long, and weakened pods begin separating from the vines before collection even starts, leaving valuable crops buried in the soil. After drying beneath the heat for several days, the second phase begins. Giant combined peanut harvesters move across the fields, functioning almost like mobile processing stations. Rotating pickup reels gather the dried plants, while aggressive threshing systems separate the peanuts from the vines at high speed. Dust storms erupt behind the machines as giant air systems strip away debris, stems, and loose soil. Clean peanuts surge upward through vibrating transfer systems before pouring directly into onboard storage bins. Meanwhile, the leftover vines are redistributed across the fields as organic fertilizer for future planting cycles. The scale is enormous. Some harvesters process several tons of peanuts every hour while replacing labor crews that once needed days to finish the same work manually. No day. A single operator sitting inside a climate-controlled cab can manage an entire harvesting operation using digital monitoring systems, onboard cameras, and automated controls. And peanuts are only one example of how harvesting technology has evolved. In California, another industry creates one of the most visually satisfying scenes in modern agriculture: pistachio harvesting. Pistachio trees require years before producing serious commercial yields, but once mature, they become part of a massive export industry supplying snack markets all over the world. During harvest season, specialized pistachio shakers move through the orchards carrying hydraulic arms lined with thick rubber padding. The machines clamp onto tree trunks before unleashing rapid bursts of vibration powerful enough to release thousands of ripe pistachios almost instantly. The sound alone is overwhelming. Branches whip violently back and forth while waves of pistachios rain downward like mechanical hailstorms. But unlike older harvesting methods where nuts crash directly onto the ground, Modern pistachio systems now deploy giant umbrella-shaped catch frames beneath the trees before shaking begins. The collection platforms unfold with remarkable speed, catching the falling pistachios before dirt, moisture, or contamination can damage the crop. Conveyors immediately transfer the nuts toward onboard storage compartments, while giant fans remove leaves and loose debris during the process. Heat creates another challenge for pistachio farms. Once the outer hull begins splitting naturally, fungal growth can spread rapidly if the nuts remain exposed too long after harvest. That risk forced orchards to adopt faster transport and cleaning systems capable of processing huge volumes immediately after collection. And nowhere is harvesting speed more critical than sweet corn production. Sweet corn contains extremely high sugar levels when fully ripe, but those sugars begin converting into starch almost immediately after harvest. That transformation changes both flavor and texture surprisingly fast, which is why giant sweet corn harvesters operate with almost military coordination during peak season. Massive machines roll through the fields, gripping thick corn stalks with hydraulic feeding systems, while rotating blades slice entire rows at high speed. Golden ears surge upward through spinning rollers that strip away excess leaves and husks before the cleaned corn transfers directly into refrigerated trailers moving alongside the harvesters. The process happens incredibly fast. Corn can move from standing in the field to cold storage within minutes. The United States alone, hundreds of thousands of acres of sweet corn are planted annually, but most consumers never realize how little of it actually reaches supermarket produce sections fresh. The majority moves directly into industrial freezing and canning facilities operating nonstop throughout harvest season. Inside those facilities, giant cooling systems lock in sweetness before the natural sugar breakdown accelerates further. Conveyor networks, freezing tunnels, and packaging systems continue running around the clock while truckloads of fresh corn arrive one after another from the fields. And then there are sunflowers. One of the most visually dramatic crop transformations in agriculture. During summer, sunflower fields glow bright yellow beneath the sun. But by harvest season, the flowers darken, bend downward, and dry into heavy seed-packed heads waiting for collection. Then the harvesters arrive. Sharp metal guides pull the towering stalks into giant cutting systems, while powerful threshing drums strip thousands of seeds from every flower head in seconds. Dry husks explode outward into the wind, while streams of glossy black sunflower seeds tumble through the machinery like flowing gravel. Behind the harvesters, entire fields disappear row by row. What once looked like endless yellow landscapes quickly transforms into harvested ground, while millions of sunflower seeds begin their journey toward cooking oil production, snack foods, livestock feed, and large-scale food manufacturing systems across global markets. Modern harvesting is no longer just about collecting crops. It has become a highly synchronized operation where machinery, timing, climate, logistics, and product quality must all function together without interruption. Among all fruits moving through the global food industry, few are more fragile than raspberries. Their soft texture, hollow structure, and delicate skin make them extremely difficult to harvest, transport, and process at large scale. Yet every year, farms in Washington state alone produce tens of thousands of tons of raspberries destined for freezing plants, dessert factories, jam production lines, and international food markets.
At first glance,
Raspberries look almost too delicate for industrial agriculture. But behind that bright red appearance lies one of the most tightly controlled processing systems in modern food production. Unlike many other berries, raspberries naturally separate from their core when ripe, leaving a hollow center inside every fruit. That tiny cavity may look harmless, but it can also trap moisture, mold spores, insects, and microscopic contaminants surprisingly easily. Even short transport delays can trigger juice leakage, softening, fungal growth capable of damaging huge batches of product. That vulnerability forces raspberry farms to move with incredible discipline during harvest season. In large commercial growing regions across Washington and California, Modern harvesting machines now operate across enormous berry fields almost non-stop during peak production weeks. Some systems cost more than $200,000 and function like mobile fruit processing platforms moving directly through the rows. Fiberglass shaking rods vibrate the raspberry canes carefully enough to release only ripe fruit while leaving immature berries attached to continue developing. Thousands of raspberries drop onto padded collection surfaces before transferring into sorting systems integrated directly into the harvester itself. At the same time, powerful air jets remove leaves, insects, and debris, while onboard workers inspect the berries continuously as the machines move through the fields. From above, the operation looks almost unreal. Bright red raspberries stream across synchronized sorting systems while harvesting machines crawl steadily through the rows beneath clouds of dust and drifting leaves. But despite all this automation, premium raspberries often still require hand harvesting. The fruit bruises extremely easily under pressure, and even small compression marks can spread rapidly during cold storage and transport. Workers carefully place individual raspberries into trays by hand, handling them more like fragile glass ornaments than agricultural products. That contrast defines much of the modern raspberry industry. On one side, high-capacity mechanical harvesting systems capable of processing enormous volumes quickly. On the other, delicate manual labor still required for the highest value markets. Once harvested, the raspberries immediately begin another carefully controlled journey. Refrigerated trucks are positioned beside the fields before harvesting even starts, because the fruit cannot tolerate long exposure to heat after collection. The filled trays are transported directly toward nearby processing plants, where automated unloading systems take over almost immediately. Inside the facilities, the handling process becomes even more controlled. Specialized forklifts move pallets slowly into receiving zones while automated platforms gently tilt each tray onto transfer systems designed to minimize impacts and crushing. No violent drops. No sudden collisions. Every movement is tightly controlled to preserve the structure of the fruit. Then comes cleaning. Unlike apples or citrus fruits that can tolerate aggressive washing systems, raspberries require extremely gentle water sprays operating at very low pressure. Excessive force can rupture the fruit instantly and destroy its market value. The visual effect is mesmerizing. Bright red raspberries cascade through polished steel systems, while vibrating platforms keep every berry separated and intact. Water filtration systems continuously recycle and purify the cleaning streams, while workers positioned under bright inspection lighting remove damaged or discolored fruit moving through the line. And behind the satisfying visuals lies constant pressure, a refrigeration failure, contamination issue, or sorting mistake inside a major berry facility can trigger expensive product recalls affecting supermarkets across multiple regions. Because of that risk, modern raspberry factories operate under strict hygiene monitoring systems almost continuously. Then comes one of the most important stages in the entire process: rapid freezing, instead of cooling the berries slowly. Industrial freezing systems reduce temperatures extremely fast to preserve texture, color, and flavor before large ice crystals can damage the fruit internally. The raspberries travel through ultra-cold chambers on vibrating transfer lines that prevent the berries from sticking together during freezing. Within minutes, millions of frozen raspberries emerge perfectly separated and ready for packaging. Workers perform one final inspection while automated weighing and sealing systems prepare the product for distribution. Every package receives tracking labels capable of identifying harvest locations, processing batches, and production dates within seconds. But frozen berries are only part of the raspberry industry. Some of the highest quality fruit continues toward jam production, where giant heated kettles blend raspberry puree with sugar under tightly controlled temperatures. The thick crimson mixture slowly concentrates while industrial mixers keep the texture smooth and consistent throughout cooking. Unlike many fruits that lose their color during heating, raspberries naturally retain their deep red-purple appearance because of their high anthocyanin content. Under the factory lights, the glowing mixture moving through polished steel pipes almost looks molten. Automated filling systems then inject the jam into sterilized glass jars with remarkable consistency before sealing. Labeling and packaging systems prepare the final product for supermarkets around the world. And all of it begins with one of the softest fruits in agriculture, surviving a production environment built around speed. Hygiene, synchronization, and extremely careful handling. California now produces most of the world's almonds through one of the largest and most technologically advanced agricultural systems on Earth. Every year, enormous almond orchards supply global snack brands, desert factories, bakeries, and food manufacturers with millions of tons of product moving through an industrial network worth billions of dollars. And every season begins with a massive migration. As almond trees burst into bloom across California's Central Valley. Millions of beehives arrive by truck from across the United States. Billions of bees spread through the orchards, pollinating the flowers nonstop during the short blooming period that determines the success or failure of the entire harvest. Months later, the calm orchards transform completely. Giant almond shakers move between the rows, carrying hydraulic arms powerful enough to unleash violent bursts of force against the trees. Thick clamps lock onto the trunks before thousands of almonds suddenly explode downward all at once. The ground erupts beneath the orchards. Dust clouds burst into the air while huge waves of almonds hammer against the dry soil like mechanical rainstorms. Modern shaker systems can harvest enormous sections of orchards with astonishing efficiency, replacing large labor crews that once relied on dangerous manual harvesting methods. But once the almonds hit the ground, another synchronized operation immediately begins. Specialized sweepers equipped with rotating brushes move through the orchards, organizing the almonds into long, clean windrows before large pickup harvesters begin gathering the crop using conveyor intake systems and high-powered airflow separators that strip away leaves, twigs, and debris during collection. Within minutes, truckloads of almonds begin leaving the orchards, headed toward high-capacity processing facilities active around the clock during peak harvest season. And the factories themselves feel closer to automated manufacturing plants than traditional food processing centers. When almonds first arrive, they still contain shells, dirt, whole fragments, and field debris. Giant cleaning systems immediately begin separating unwanted material using combinations of vibration systems, airflow channels, and mechanical sorting equipment. Then the almonds move into one of the most advanced inspection stages in modern food production. High-resolution imaging systems scan enormous volumes of almonds continuously, detecting tiny cracks, shell damage, discoloration, and defects almost invisible to the human eye. Computer-guided sorting systems instantly calculate the exact position of defective almonds before robotic ejectors remove them from the line with incredible speed. Thousands of sorting decisions happen every minute. And yet human inspectors still remain part of the process, checking for subtle irregularities automated systems occasionally miss. Before packaging, the almonds pass through steam pasteurization systems that eliminate harmful bacteria while preserving flavor and texture. From there, the crop separates into multiple production lines. Premium whole almonds are sealed for export while smaller kernels continue toward almond butter production. Industrial baking ingredients, snack foods, and confectionery processing. Nearby, another production line transforms almonds into premium chocolate and toffee products. Roasted almond pieces are coated in flowing caramel and warm chocolate before cooling into glossy bite-sized candy. Rivers of melted chocolate glide through polished steel systems, while golden roasted almond fragments rain downward onto freshly coated candy moving steadily beneath the machinery. And this is what the modern almond industry has become. A massive synchronized network where orchards, harvesting machines, AI inspection systems, automated processing lines, and global food distribution all operate together at industrial scale. Endless pineapple fields stretch across tropical landscapes beneath the blazing sun, their sharp green crowns forming enormous geometric patterns visible from the air. Every year, countries like Costa Rica produce millions of tons of pineapples destined for supermarkets. Juice factories, canning plants, and food manufacturers across the world. But behind the bright colors and sweet flavor lies one of the most physically demanding harvest operations in modern agriculture. Unlike many fast-growing crops, pineapples require extraordinary patience. Single fruit can take nearly 2 years to fully mature. During that time, farms maintain irrigation systems, fertilizer schedules, pest control operations, and soil management programs long before the harvest season finally begins. And once the fruit reaches peak ripeness, the pressure increases immediately. Pineapples harvested too early lack sweetness and aroma. Wait too long, and the fruit softens too much for industrial slicing, packaging, and overseas shipping. Growers constantly monitor color, sugar content, and ripeness conditions to determine the exact moment harvesting should begin. But even when the fruit is ready, the work itself remains brutal. Every pineapple plant is surrounded by razor-sharp leaves capable of slicing exposed skin with ease. Workers move through the fields wearing gloves, face shields, and heavy protective clothing while cutting pineapples manually beneath intense tropical heat. Yet modern plantations are rapidly transforming even this stage of production. Conveyor-assisted harvesting vehicles now move directly beside workers through the rows. Instead of carrying heavy loads across enormous fields, workers simply cut the fruit and place it onto moving transfer belts that automatically carry the pineapples. Into onboard storage systems, the efficiency gains are enormous. Some plantations now harvest several times faster than traditional manual operations while reducing worker fatigue and minimizing fruit damage during collection. Soon afterward, truckloads of freshly harvested pineapples begin heading toward enormous processing facilities running day and night throughout peak season. This is where the transformation becomes even more impressive. At the receiving stations, pineapples enter giant water channels used for the first major quality inspection. Fruit with ideal ripeness and density behaves differently in the water while damaged or walled. Lower quality pineapples are separated rapidly before processing continues. Next comes industrial cleaning. Rotating wash systems, spray tunnels, and disinfectant treatments clean thousands of pineapples every hour, while transfer systems move the fruit deeper into the facility. Conveyor motors hum constantly while streams of water crash across endless waves of pineapples traveling through polished stainless steel machinery. But not every pineapple follows the same path. The best-looking fruit is separated for premium export markets where appearance carries enormous commercial value. These pineapples receive a thin, edible wax coating that helps preserve moisture and creates the glossy finish consumers recognize in supermarkets worldwide. Workers then inspect the fruit carefully, sorting it by size, color, ripeness, and external quality before packaging systems prepare the pineapples for overseas distribution. Meanwhile, the remaining harvest enters one of the most satisfying food processing operations in modern agriculture. Automated peeling systems equipped with ultra-sharp blades and sensor-guided cutting mechanisms begin, stripping away the thick outer skin within seconds. Each pineapple rotates rapidly while the cutting systems adapt automatically to different fruit sizes, preserving as much edible flesh as possible during processing. Then comes the coring stage. Hollow drilling systems punch directly through the center of each pineapple, removing the dense fibrous core in one clean motion before the fruit advances towards slicing systems operating at industrial pace. Perfect pineapple rings begin emerging one after another with remarkable consistency. The slices glide smoothly across transfer systems before dropping neatly into cans waiting below. Sweet syrup floods the containers, while sterilization chambers prepare the product for long-term storage and retail distribution. Nearby, separate production lines transform pineapple chunks into fruit cups. Frozen products, desserts, dried snacks, and bottled juice distributed across commercial food networks every day. Even the leftover waste rarely goes unused. Fibers, peels, and processing scraps are often recycled into fertilizer, livestock feed, or secondary industrial products as producers continue pushing efficiency across the entire operation. The entire system functions like a giant synchronized network where harvesting, processing, packaging, and shipping connect almost seamlessly from field to factory. But before any of this machinery can begin operating, the process always starts back in the soil itself. Before planting, giant tractors loosen hardened tropical ground while workers and planting systems carefully position young pineapple shoots into evenly spaced rows. Drip irrigation networks deliver water and nutrients directly toward the roots, while automated fertigation systems optimize growing conditions throughout the long production cycle. Now, artificial intelligence is beginning to reshape even this stage of agriculture. Across enormous farming regions, machines are already planting, monitoring, irrigating, harvesting, sorting, and packaging food with less human involvement than ever before. What once required thousands of workers can now be coordinated by automated systems operating day and night across entire agricultural networks. And as artificial intelligence continues advancing, the farms of the future may no longer look like traditional farms at all. They may function more like giant automated food factories stretching across entire landscapes. And the most surprising part is that this transformation is no longer decades away. It is already happening right now.